So hello everybody, it's a pleasure to meet all of you in another seminar, Lógicos in Quarentena, promoted by the Brazilian Logic Society and the interest group in Logic Interest Group of the Brazilian Computer Society. We are now joining the Logic Supergroup, and it's a pleasure to introduce Professor Rui de Queiroz, who will talk about computational paths and the calculation of fundamental groups. Rui, thank you very much for joining us in the seminar.
Thanks, Bruno. Thanks for accepting my offer, because this time you didn't invite. It was myself who offered it for the series, which I have to say is such a nice initiative, such a nice idea. I shall be talking to you about the kind of work I've been doing with a couple of students of mine in the so-called, in the application of intuitionistic type theory to topology. And I will start by reminding those who probably, I don't know how many of you know, Rolf Schock Prize in Logic was awarded to two Swedish logicians, Dag Prawitz and Per Martin-Löf. And if you allow me to read the citation at the web page, it says, Rolf Schock saw beauty in logic and philosophy, as well as mathematics, art, and music. This year, his prizes are being awarded to two Swedish logicians, a Russian mathematician, a Belgian artist and architect, and a Hungarian composer. The prize is worth 400,000 krona per category, a total of 1.6 million Swedish krona. The Rolf Schock Prizes have unusual large breadth. The foundation that was created after the death of Rolf Schock decides who will receive the prizes in partnership with no fewer than 3 Swedish academies: the Royal Swedish Academy of Science, the Royal Academy of Fine Arts, and the Royal Swedish Academy of Music. The Schock Prizes recognize people who have made outstanding contributions in these 4 areas in which Rolf Schock was particularly interested. It's a great honor to the participating academies to celebrate these creative individuals at the prize ceremony on 19th of October and other events in association with this, says Goran Hansson, Secretary General of the Academy of Science and Chair of the Schock Foundation. Then Logic and Philosophy, and the 2020 Rolf Schock Prize in Logic and Philosophy is awarded to Dag Prawitz from Stockholm University for proof theoretical normalization in natural deduction, and Per Martin-Löf for the creation of constructive type theory. And then the citation for those two come like this. Logic is the study of what makes some arguments or inferences valid and others not. Dag Prawitz and Per Martin-Löf from Stockholm University are emeritus professors, respectively, specializing in proof theory and constructivist philosophy of mathematics. They are both members of the Royal Swedish Academy of Sciences and have been nominated by scholars all over the world. I will skip Dag Prawitz and go straight to Per Martin-Löf. Initially, Per Martin-Löf also worked in proof theory, cooperating closely with Prawitz. In the 1970s, he created a constructive version of type theory, a formal language in which it is possible to express constructive mathematics. Here, a proof of a mathematical statement can be regarded as a program for verifying this statement. Constructive type theory also functions as a powerful programming language and has had an enormous impact in logic, computer science, and, I will emphasize this, recently, mathematics. So what I will talk about today was try to show you how I think one aspect in which intuitionistic type theory had an important impact in mathematics, especially via the work of two students of mine, one of them mathematician, the other one theoretical computer scientist. Especially, what is so important, what was the tools through which intuitionistic type theory, to my understanding, had an impact in mathematics recently. Then I will emphasize especially one aspect of the type theory, which is to formalize what is called then proofs of equality, by introducing in 1973 a framework in which a formalization of the logical notion of equality via the so-called identity type. Martin-Löf type theory allows for a surprising connection between term rewriting and geometric concepts such as path and homotopy. The impact in mathematics has been felt more strongly since the start of Vladimir Voevodsky's program on the univalent foundation of mathematics around 2005, joined by Steve Audi in building an approach to have referred to in 2007 as homotopy type theory. So then it's focusing on the formalization of proofs of equality that I will then talk about these notions which are in the title, computational path and calculation of fundamental groups. It really had to, had to come from a mathematical genius like Vladimir Voevodsky to really make a difference in really trying to bring all the tools of type theory, in particular these so-called identity types, into helping to formulate and formalize some of the things that one finds in homotopy type theory, homotopy theory, which is an area which is so important in mathematics. And then I quote from a talk that he gave at the Institute for Advanced Study in Princeton. He's talking about the so-called isomorphism invariance principle. He says one of the keystones of contemporary mathematics is the isomorphism invariance principle. For any statement P about X, and any isomorphism X is isomorphic to X prime via this isomorphism phi, there is a statement P of phi about X such that P holds if and only if P of phi holds. The equality problem in formalization comes in part from that when one encodes X and X prime, the isomorphism is lost. There is more to the equality problem than isomorphism invariance. Equality is good notions for elements, individuals, but fails for collections. Isomorphism is a good notion for collections, but fails for collections of collections. Then he says, this leads to a theory of iterated n-equivalences, which are the correct replacements for such iterated collection. This was in a talk which is on YouTube, Foundations of Mathematics and Homotopy Theory, in 2006. And then I'll take you to quite an interesting talk by, well, I saw the slides, I didn't see the talk, by Michael Schumann from University of San Diego on what he called then justification why homotopy type theory, which arises from this idea of interpreting the so-called identity types as spaces of path in the sense of homotopy theory. He calls a high-level language for invariant mathematics. Homotopy type theory is a high-level abstract framework for working with sameness, really to address this kind of problems that Vladimir was talking about. Equality is maybe good for individuals, isomorphism may be good for collections, but then it's not so good for collections, and so on. So in the end, what would be the best, best notion to deal with equivalencies in higher order. And then Mike Schumann mentions about sameness. One can talk about, for example, two groups are the same if they are isomorphic. Two topological spaces are the same if they are homeomorphic. Two categories are the same if they are equivalent. Two lambda terms are the same if they are convertible to one another. Two sets are the same if they have the same extension. Two mappings are homotopically the same if one can be continuously formed into the other. And then I quote now from an article in the Wikipedia. Up again this so-called topologist joke, which compares a coffee cup and a donut. Are they the same? Then the article in Wikipedia, which is quoted in a talk by Dick Grayson in the a talk he gave at Princeton on the obituary of Vladimir Voevodsky. He says, an often repeated mathematical joke is that topologists can't tell the difference between a coffee cup and a donut, since a sufficiently pliable donut could be reshaped to the form of a coffee cup by creating a dimple and progressively enlarging it while preserving the donut hole in the cup's handle. Then, how do people in algebraic topology, in particular in homotopy theory, deal with this notion of sameness of spaces? And then I bring again a quote from Wikipedia, which says, in modern mathematics, it's common to study a category by associating to every object of this category a simpler object that still retains sufficient information about the object of interest. Homotopy groups are such a way of associating groups to topological spaces. The link between topology and groups lets mathematicians apply insights from group theory to topology. Then that's where the term here is called homotopy groups, but the fundamental group is one of the kinds of homotopy groups one can have. That's then referring to the title of my talk. Now, from the Wikipedia again, but I can also find in textbooks on algebraic topology, one can see the following. Homotopy groups are used in algebraic topology to classify topological spaces. The first and simplest homotopy group is the so-called fundamental group, which records information about loops in a space. Intuitively, homotopy groups record information about the basic shape or holes of a topological space. Topological spaces with different homotopy groups are never equivalent or homeomorphic, but topological spaces that are not still have the same homotopy groups. Then the emphasis here is mine, referring to the calculation. Calculation of homotopy groups is in general much more difficult than some of the other homotopy invariants learned in algebraic topology. So what I'll try to bring to you is a view in which I can bear witness to the impact, the recent impacts of intuitionistic mathematics, in the sense that it's giving us, via the so-called identity types, a way in which these calculations can be made much easier, because it's then giving a formal framework, a way in which to reason about expressions which will denote paths in order to actually not just calculate homotopy groups, but also prove homotopy groups. And I want to bring, what I saw is this student of mine who is a mathematician who was interested in algebraic topology. What he did was taking the formalization of the identity types, which is not exactly, we will talk about this later on, is not exactly like the one in the so-called book entitled Homotopy Type Theory. There are slight differences. But what he did was taking some of these classical surfaces like torus, like the two-hole torus, like the Klein bottle, a projective space, like the Möbius strip and the cylinder, and using the formalism to actually calculate and prove the so-called fundamental groups of these surfaces. And so that I could see concretely, and he was telling me as a mathematician that in textbooks, to prove these homotopy groups is usually something rather difficult, as you could see in the quote from the Wikipedia. And then what he's saying, and he's actually doing it by himself, he's written papers about it, is how this formalization of the so-called identity type in type theory makes it substantially easier to do this, to not just to calculate, but also to prove using the formalism. And this is a kind of a little bit of an abstract. There are a paper that he posted on arXiv, which says we show a surprising connection between the label natural deduction theory, which is a kind of a variation that we defined of the so-called intuitionistic type theory, developed by now, which has been developed by the use of so-called computational paths, and we'll see what these are, as labels on the use of the so-called term rewriting systems in the label natural deduction for equality as the logical rules between these computational paths. We now show a surprising connection to obtain one of the main results of algebraic topology, the calculation of the fundamental group of the circle. So in a series of posts to the arXiv, this student of mine, especially this with the first author, Tiago Veras, he actually carried on the work done by the second author, Artur Ramos, who was a computer scientist and did the basis for this formalization of computational paths to do a lot of these calculations and then show indeed how indeed the notion of identity type can make it a lot easier to calculate. And the idea, giving a rough idea, he has to define for each surface what is a loop. And then, when he say, the first thing one should notice that this definition does not use only the points of the type S1, which is a circle, but also a base computational path called loop between this one inductive type. Then the emphasis is mine here. Our approach differs from the one developed in the book, the hot book, Homotopy type theory book, on the fact that we do not need to simulate path spaces between those points, since we add computation back to the syntax of the theory. So one of the things that we'll see a bit later on is that one aspect of the formalization given of identity types given by Martin-Löf was that he did not introduce the identifiers for the paths, because the idea was the identity types would be inhabited by paths that would connect two elements in the type. So A and B are elements of a type X, and they are equal because there is a way to go from A to B via a path. And what would this path be? Would be in the formal theory, would be a rewriting path. So what we did, this comes from a much earlier work. We reformulated the identity type, so to speak, introducing an explicit entity for type for the path which would inhabit the identity type. And that's the difference that he's emphasizing. I'm emphasizing here in boldface. But then I'll bring you again to this, path. What is a path? I've already mentioned. One can think of the path between terms in lambda calculus, and I'll bring this slide up, just taking a picture from the original paper by Church in 1936, and he defines what right at the bottom of the quotation says. A is no, it's what is it? Any finite sequence of these operations, which operations are these? 1, 2, and 3. They are alpha contraction, the just change of bound variables, beta contraction, and the inverse of beta contraction. Any finite sequence of these operations is called a conversion. You notice that by taking the symmetric or the transitive closure of this contraction relation, you get this relation of conversion. And if B is obtainable from A by a conversion, we say that A is convertible into B, or A conv B, A convertible to B. So A is declared to be equal or equivalent to B if there is a path. In this case, a rewriting path. Now notice that equality here is taken to be the reflexive symmetric transitive closure of the one-step contraction, which is the symmetric closure of the rewriting path. So it's interesting how one seeing this path as being, these rewriting paths, thinking of as being elements of the so-called identity types, you prove that A is equal to B in formal theory if you can construct a path. Yet it is a kind of reversible path because symmetry is allowed. So having this rewriting path, one can interpret, which is done via the so-called homotopy type theory, or the homotopy type theory, semantics of type theory, can be interpreted as a path, as a path in the geometric sense. So it's amazing how you can see connections and bridges between areas which are so apparently so far apart. Computation, algebraic topology, logic, because they are proofs of equality. Higher categories, we'll see a bit later on why. Higher algebra, omega groupoids, paths as structured preserving maps. And the equivalencies of paths can be also dealt with in the formal framework of the identity types, because we can think of equality between equality paths, and this can be iterated up at infinity. Here I just bring a quote from a traditional textbook on lambda calculus. P is convertible to Q via not just beta, but here is also including the so-called eta contraction. If there is a series, perhaps empty, but finite, which connects, which allows you to start from P and end with Q. So it is, in fact, it's called a series, but one can think of it as a path. Now, how does this fit together in the so-called type theory? Just to remind you, the so-called paradigm of formula as types, which is started in 1934, when Curry came up with an early version of so-called type inference for the combinators of combinatorial logic, which also showed that the types of combinators could be seen as axioms of intuitionistic implicational logic. So alpha arrow beta could be read as the type of functions from type alpha to type beta, and also the formula alpha implies beta. So the axioms of intuitionistic or constructive implicational logic end up being the so-called type of the basic combinators. And in 1969, Howard came up with an extension of this interpretation of, types as propositions or propositions as types via the notion of a dependent type, or a dependent product of types, and dependent sum. And Martin-Löf, which as far as I know, he's spent, I guess, a year, a postdoc or some kind of visit in Chicago with Howard. He then, I guess, perhaps discussed a lot of this idea with Howard, and came up in 1972 with what he called the type theory, extending formless types with natural numbers and universes, and finite types, in fact. In 1973, then that's the big step, which apparently remained unnoticed or remained maybe somehow in the background in 1973, where he introduced then the so-called identity types, which basically says that this is to formalize in the framework of formless types, proofs as program, as the types of identity or equality between terms. And this remains so somehow forgotten in a way, and in fact, even Martin-Löf himself had different formulations in later formulations of type theory after 1973. He, changed a little bit the rules of identity types, which made a little bit confusing. One could see two so-called versions of identity type: the so-called intentional identity type and the so-called extensional identity type. This the two of them were actually mixed in this publication in 1979, Constructive Mathematics and Time and Computer Programming. But then I guess what really changed quite significantly was in 1994, when Hoffman Streicher presented at LIX 94 an interpretation of identity type into a groupoid, just to refute the so-called uniqueness of identity proofs. But then from 1994 until the 2000s, beginning of 2000s, little was talked about, was a bit somehow in the background, the so-called identity type. And then I quote from a workshop organized in 2006, and at this point was already in scene Vladimir Voevodsky's interpretation into homotopy theory. The workshop is called like this: the identity type, the type of proof objects for the fundamental proposition of equality, is one of the most intriguing, this is my emphasis, constructions of intentional dependent type theory, also known as Martin-Löf type theory. Its complexity became apparent with the Hoffman-Streicher groupoid model of type theory. This model also hinted at some possible connections between type theory and homotopy theory in higher categories. Exploration of this connection is intended to be the main theme of the workshop. In 2007, it was still around this sort of cloud of mist. What is this identity type in type theory? Michael Schumans in 2017 says in a paper called The Logic of Space, for many years, the most mysterious part of Martin-Löf's type theory was the identity type. Now, again, when one thinks about these elements of the terms in type theory as derivations, one can see there is a connection, and this is, I quote from a blog by Phil Wadler, on an interview with Howard, whether he thought of the elements of the types as derivations of proofs or coding of the proofs, which then allows one to see this, quite easily, this sort of the bridge between proof equivalence and term equivalence. From a call for a trimester in Bonn, I just quote you, allow me to read this. Type theory, originally conceived as a bulwark against the paradox of naive set theory, has languished for a long time in the shadow of axiomatic set theory, which became the mainstream foundation of mathematics. The first renaissance of type theory occurred with the advent of computer science and Bishop's development of practice-oriented constructive mathematics. It was followed by a second, quite recent one, not only champions type theory as a central framework for achieving the goal of fully formalized mathematics amenable to verification by computer-based proof assistance, but also finds deep and unexpected connections between type theory and homotopy theory. Constructive set theory in mathematics distinguishes itself from its traditional counterpart, classical set theory and mathematics based on it, by insisting that proofs of existential theorems must afford means for constructive an instance. Constructive reasoning emerges naturally in core areas of mathematics and in the theory of computation. The aim of the trimester Hausdorff in Bonn was to create a forum for research on and dissemination of exciting recent developments, which are central importance to modern foundation mathematics. Then, as many people know, the first mathematics book, which was sort of open source, is this amazing work, which is which was produced in the Institute for Advanced Study in 2013 was the first edition. And if one has, takes a look at the sort of authors page, you see that there are in fact 27 main participants and 58 contributors. The latest version, as far as I can tell, was made available in April 15, 2020, and essentially says from its introduction of the preface, homotopy type theory is a new branch of mathematics that combines aspects of several different fields in a surprising way. It's based on a recently discovered connection between homotopy theory and type theory. Homotopy theory is an outgrowth of algebraic topology and homological algebra with relationships to higher category theory, while type theory is a branch of mathematical logic and theoretical computer science. Although the connections between the two are currently the focus of intense investigation, it is increasingly clear that they are just the beginning of a subject. They will take more time and more hard work to fully understand. It touches on topics as seemingly distant as the homotopy groups of spheres, the algorithms for type checking, and the definitions of weak infinity groupoids. And to my understanding, these connections are possible, as far as I can see, because one can see the rewriting sequences according to the conversion relation given by Church in lambda calculus as a path. And this can be a concrete path which can be interpreted as a geometric notion. Where did he first start? Voevodsky says that the first use of so-called homotopy lambda calculus was on a tech report, which is on the web, called Notes on Homotopy Lambda Calculus, started 18th of January 2006. And I remember I was in Stanford in 2006, and I saw a post of a seminar which was going to be given by somebody named, or a Russian name I'd never heard of, on the homotopy lambda calculus. And it was middle of 2006. I don't remember exactly. I think it was spring term. And then he says, in this paper, it suggests a new approach for the foundation of mathematics. A key development totally unnoticed by the mathematical community occurred in the 70s, when the type lambda calculus was enriched with the concept of dependent types. Later on, Steve Oddy from CMU joined Voevodsky in opening up a sort of a research program called, then the first occurrence of this term is in a seminar in 2007 in the 86 peripatetic seminarship in logic, where he referred to what was then called homotopy type theory. Of course, what they have done in the book, there are beautiful proofs of known theorems. They are not new proofs. They are not new theorems. They are new proofs of a lot of results in the Blake and Massey theorem, and so on. Anyhow, this can, then justify what he's saying here. Homotopy type theory can also serve as a foundational system for mathematics, whose basic objects are infinity groupoids rather than sets. And in several of his talks, which most of them are on YouTube, Vladimir Voevodsky tries to argue how important it is to take infinity groupoids as basic objects for the foundation of mathematics. Now I bring back again, just to restore the mood we were in the beginning, about this calculation of fundamental groups. I quote from a really nice textbook by Alan Hatcher on algebraic topology. It says, one of the main ideas of algebraic topology is to consider two spaces to be equivalent if they have the same shape, so to speak, in a sense that is much broader than homeomorphism. In the talk that Dick Grayson gives, which is on YouTube, is a beautiful, I recommend to those who like this topic. He, for example, mentions that Voevodsky didn't see why one shouldn't see, for example, the torus as being, so to speak, the same as a circle. But then you can't do it via homeomorphs because there are different dimensions, for example. But anyhow, the fundamental group of a space X will be defined so that its elements are loops in X, starting and ending at a fixed base point, x0 in X. But two such loops are regarded as determining the same element of the fundamental group if one loop can be continuously deformed to the other within the space X. Then I go again to the title of my talk, which is computational paths. What are computational paths? We are talking about an enriched syntax of type theory in which not just the terms, they have a counterpart in the form of theory, but also the paths themselves. So one can talk about not just rewriting, but rewriting paths, because paths will be in a language of paths. So this can be interpreted then, one path is could be usually. One can also show that two spaces are not homeomorphic by showing that their fundamental groups are not isomorphic, since it will be an easy consequence of the definition of the fundamental group that homeomorphic spaces have isomorphic fundamental groups. Time is flying. So as I mentioned in the beginning, in a series of posts to the archive, these two students of mine have been playing around with, for example, proving the fundamental group of a circle is the integer, the cylinder, the Mortgage Grand, all these classical surfaces. Audi, in a paper in 2016, refers to as if the homotopy type theory being a new field devoted to a recently discovered connection between logic and topology, more specifically between constructive type theory, which was originally invented as a constructive foundation for mathematics, and now has many applications in theory of programming languages and formal proof verification, and homotopy theory, a branch of algebraic topology devoted to the study of continuous deformations of geometric spaces and mappings. The basis of homotopy type theory then is an interpretation of the system of intensional type theory into abstract homotopy theory. As a result of this interpretation, one can construct new kinds of models of constructive logic and study that system semantically, for example, proving consistency and independence results. Conversely, constructive type theory can also be used as a formal calculus to reason about abstract homotopy. Now, being very concrete now, and now again, going back to this idea that we want to to make these bridges between computation and homotopy, a lambda term, a very concrete lambda term, which is not in normal form, can be reduced to a normal form via different orders of rewriting. Of course, by the Church-Rosser theorem, if this term has a normal form, it is a unique one. But which of the sequences is not necessarily, in fact, the theorem says, regardless of the order of you choose the redexes to contract, the normal form should be unique. So in this case, the same terms, I'm showing you three sequences, three paths between the normal and sequence of contractions from the initial term to the final term. Thus, in the formal theory of lambda calculus, the term is declared to be equal in the sense of convertible, going back to Church. Now, some natural questions arise. Are the sequences themselves normal? What is it? What is a normal sequence? What are the non-normal sequences? How are the latter to be identified and possibly normalized? And then we go into analyzing, what kind of redundancies, one can say, bringing in a notion from proof theory that you can identify between paths, not between terms, but between paths. One obvious one is if one uses, for example, symmetry. If you take the symmetric closure here, you turn this into an equality, you can say, well, see, this is equal to that, then this is equal to that. And then you can make a longer, of course, unnecessarily long path. But there are lots more sequences of contractions which can be defined to be redundant, to be unnecessarily long by analyzing the proof logically by proof theory, by the so-called natural deduction proof system. So from the analysis of the proofs, one can then analyze the terms and then analyze the possible normal sequences of equality proofs or non-normal and how to normalize them. And just to remind you, the so-called BHK interpretation. Now, if one thinks of a statement, a proposition like T1 is equal to 2, what is it? Because if a proof of a conjunction is an ordered pair, if a proof of disjunction is a sort of an injection term, if a proof of an implication is a function, the same for an universal quantifier, similar for this dependent sum, for extent. So what is a proof of the proposition that T1 is equal to T2? What would be a direct or canonical proof of an equality? And what is an equality between paths? Because if one thinks that, for example, if T1 and T2 are equal because there is a path, but there may be another path between T1 and T2. How does one compare two paths? If one has the term for path, the entity in the formal system, one can then extend and iterate these equivalences, equivalence between elements, equivalence between paths, which are homotopies, then equivalence between homotopies, and so on. So in type theory, one has these two main kinds of judgment. X is a proof of A, or X is an element of A, or X is an equal element of Y, both are of type A. But this equality here is from a rewriting kind of a rewriting notion. So this is the so-called definitional. So when you can talk about equality as a statement, then it comes in the notion of the identity type. Identity type is, it can be seen as a proposition which says it is true if there is a sequence of conversion or sequence of contraction and so on, which takes you from X to Y. Suppose P is an element of this type, identity in A between X and Y, is P is interpreted as a path. And in the original system that Martin-Löf defined in 1973, as I mentioned before, the only identifier for the elements of the identity type was a constant of reflexivity. And it's curious, I took it from an email group, a bit where Martin Skardor interviews Vladimir Voevodsky about this aspect of the identity type of Martin-Löf's original type theory, where he talks about the paths as not part of the syntax. This is clear from an answer given by Voevodsky for the following question. Skardor says, what was your first reaction when you first saw the type of identity? Did you immediately connect it with path spaces? And then Vladimir Voevodsky said, not at all. I did not make this connection until late 2009. And this is my emphasis. All the time before it, I was hypnotized by the mantra that the only inhabitant of identity type is reflexivity, which made it useless from my point of view. So what I then would like to say is exactly this, this aspect recalled by Voevodsky, which makes it, make the formulation of the syntax of the identity type very complicated, and of course everything is done via the so-called semantics, so to speak. The paths are not citizens of the formal framework. They have to be dealt with outside. And so the group that worked on the book, the HoTT book, they construct their proofs of the fundamental groups of some surfaces. I don't know how many of them they do. They use a method which they call encode-decode. If I may, I'll bring this. See if I can find it here. Here. In the HoTT book, path terms are not in the syntax. So they say to characterize a path space, the first step is to define a comparison between Foundation code that provides a more explicit. Then this explicit is a key word here, because what we prefer to do is to use an explicit identity. Instead of working with judgments like this in type theory, we introduce a so-called an entity, a formal entity, to actually denote those paths, and then define rewriting rules for those entities. Like, for example, here. Like here, for example, if x is equal to x, because of reflexivity, we actually introduce some constants for reflexivity, symmetry, and all these beta, alpha. So if x is equal to x, they are both elements of A, then applying symmetry to this path, which is sigma applied to both, then you get the same proof. This is a redundant proof, very trivial, but redundant. We can then contract it. We introduce a special identifier for reflexivity to reduce to this proof here. Again here, if x is equal to y because of the path R, and I apply symmetry, sigma applied to the R, and then apply symmetry again, this is clearly a redundant proof of equality, then we can contract it to a simpler proof. And then the same thing that happens with the traditional type version of type lambda calculus, we extract the term sigma rho, and then is contractible to rho. Sigma of rho, and then these associated rewritings will make up a system of rewritings, which will then serve as our proofs. For example, just now to finish, I'm actually running out of time, but in a paper, the student of mine proving the fundamental group of this circle is the integer, for example, he deals with rewriting or algebraic equivalence between paths. These are identifiers for paths, which this is a justification why this one is equal to this one, and this one is equal to this one because you apply the other rewrite, and so on. So anyhow, this is basically to have an explicit formal, explicit syntax for the paths in order to answer these three basic questions about normalizing and identifying paths. And then with this, we can even iterate and then talk about, we haven't done yet, but we have only come to the rewriting between paths. But then rewrite between paths, we haven't actually gone that far. So anyhow, I'm not going to go much longer. I've already taken too much time. I'm happy to take questions. Thank you very much for your attention. Que bom ver Veloso. Meu amigo Veloso, minha amiga Sheila. Que bom ver vocês. Um grande abraço.
Thank you very much, Rui. So, if anyone has any questions or comments, please just tell it from the chat so we can make a buffer to avoid many people talking at the same time. But first of all, thank you very much, Rui. Very nice talk.
Viva Petrúcio! Tá me ouvindo, né, Bruno?
Tô sim.
Is raising hands or are oral questions permitted?
Yes, sure.
So I
Meu
want...
amigo Walter.
Oh, Rui.
My friend Walter.
Parabéns.
Nice to see you.
Nice to see everyone
Big
around.
hug to you. Big hug to you.
You too. I have a question if nobody has.
Sure.
Sure, Walter, you can talk.
Okay, can I talk? Rui, very nice. It should be in English, I suppose, because there are many people.
Sure.
Very nice talk. I'm very much interested because one of my latest interests is Isabel and Koch and this kind of trying to think in terms of type theory for programming languages, and something that you guys know very well before me, but now I just arrived there. But I have a question concerning this nature of identity we're talking to. My basic question is the following: when people talks about identity or formalizing identity proofs, etc., what exactly are the properties they have in mind? Are they starting from a fixed family of properties for quality and sort of formalizing them, or vice versa? Are the properties of equality being formalized by the groupoids and paths and this kind of thing? Because, you know, I have a basically objection by Wittgenstein that says to say that two distinct things are equal is nonsense. And to say that two things, one thing is equal to itself is talking about nothing. So, okay, somehow he says, Wittgenstein says that there are not good enough examples of identity.
Right, a good question. Yep. I think good point, Walter. But then remember when I was talking about this distinction between what the type theory makes, which is one equality, which is essentially a rewriting quality, is a definitional. I mean, you can't. It's not something you have to prove. You just say, well, if you take the first projection of an ordered pair, you get the first element, or so to speak. This is, you actually define it. But then the identity type is this so-called the propositional content. So A is equal to B if there is something that makes you believe that A is equal to B.
Right, it's a kind of
test. Something.
Okay, it's a kind of
composition.
Test. Right, right.
Yeah, it's a composition of the definitional equalities. You see, if you want to go from A to B, you have to use the allowed, so to speak, rule. So as if I'm not really, maybe not, but you can think of the definitional equalities as a sort of a axiomatic. It's actually, you don't prove them. You just have them as the basis. From them, you build proofs or sequences of them rewritings of A to B using the definitional equalities.
I see. I mean, you don't prove it, you recognize them.
This is
right.
Yeah, this exactly. So this is easier to see in some kind of a bidimensional formal deduction system, which is the terms and the formulas. If you just have the formulas, first order it's very hard to see that because you don't reflect those things in the formulas sometimes. You just want to simply forget it. But when this system is sort of bidimensional, and one dimension takes care of this so-called intentional information, and the other one is you are only interested in the extensional, so to speak, information, which is this is true or not, this has an evidence or not. But then why? And then you go to the intentional part. Well, because of this path. And this path, in our interpretation, is not more than a kind of a church style convertibility path, which is you rewrite according to what? What rules are allowed? Well, the ones that you chose to be starting point, so definitional equalities. And this makes it very nice because then you can see that, in fact, proofs or equalities are passed. And then makes a lot of sense, this semantics in homotopy theory, because then you can iterate that. You can think about equality between paths, which are homotopies. But then you can then talk about equality between homotopies, which are kind of equality between two. And then you can iterate that. You have this globular structure, which will then make you think of this so-called, if you take the limit, you see this sort of infinity groupoid structure, which curiously, now that you talked about, Dennis Scott's D infinity, which he thought of a model initially for the type lambda calculus. And then he's later, almost a month later, he says in the paper, I realized that I could do that for the untyped version as well. Why? Because it's like an iteration. You start from natural numbers, and then you make this as D0. D1 is the space of all functions between n and n. D2 is the space between f and n to n to n to n, and so and you end up a sequence of dn's. When you take to the limit, you see that for every n, dn is embedded into d infinity. This has a kind of a globular structure as well. And a student of mine is looking at how one can extract or build an infinity groupoid with a more sophisticated topology out of the infinity, which has this so-called Scott topology. And so there's a lot of connection there. And this whole notion of these iterated equivalences that Voevodsky talks about, argues that it is important for dealing with sameness in higher order, because equality is fine for individuals, but it's not fine for collections. But then isomorphism is fine for collections, but it's not good for collections, and so on. And so one has to think of so-called identity or equivalency, or whatever name you want to give it, as not just a relation, but a whole structure. And this so-called infinity groupoid structure seems to be quite a nice one to deal with these things. Okay, fine. I have usually, for myself, for my own use, I tend to substitute the term equality with sameness. That makes more sense for me. You know, sameness. Right. I agree. Yeah. I agree. I mean, what do you mean by same? Yeah, exactly. Sameness. I mean, even when I recommend this talk by Dick Grayson about Voevodsky. It was when he had written the obituary and so on. And then he talks about this. That's in YouTube, right? YouTube, yeah. What's the name again? Just Dick Grayson. Dick Grayson, Grayson. Grayson. Okay. I'll look for it. I think it's algebraic geometry. He talks about this idea that Voevodsky, when he proved the Milnor conjecture, he was then trying to bring in this so-called motivic homotopy theory. So motivic was almost like something coming from the music. I mean, what is really fundamental to the space that you can say, this is the same as that. Like the topologists can see that a coffee mug is the same as a donut. Yeah, so that's the famous. Poor him. Yeah, that's the famous lemma, right? But there are other sameness in between geometric objects, which are even stronger than this one, than topology sameness. So it is what I think what Voevodsky left as a legacy was to say, my God, we need that mathematics, but we need a framework, we need a logic to reason about it. And this so-called homotopy type theory is, I guess, the appropriate tool for that. Good. Thank you very much. Let me pass the word to other colleagues. Muito obrigado, Rui.
So we have a question from Petrúcio.
Valeu.
Which is the relation of this with the usual foundations of mathematics as set theory? Are they incompatible?
Well, I didn't hear the beginning of the question.
Which is the relation of this with the usual foundations of mathematics as set theory? Are they incompatible?
I'm not sure. No, they are not incompatible. But what happens, Voevodsky tried to say many times, that set theory is, of course, nice, intuitive. But then when you want to talk higher equivalences, then things get complicated, because then as this so-called isomorphism invariance principle doesn't really work. And so what he would like to see, I mean, especially in later talks, was to use as a basis not sets. At some point, he even thinks that maybe categories would be basic for the foundation of mathematics, would be the basic notions. But then he says, well, set theory of categories is probably a are sort of sets in a high. I mean, it's more like sets with partial orders or ordered sets. But then, if you really want to go basic, you have to go to the so-called infinity groupoids, which are the basis for these higher equivalences.
Any other question?
You deal with these paths by using group theory, using this composition operator as the group operation. But sometimes you can't compose certain paths. So groupoid is when the operation in the group is partial.
Any other question? Well, so I will stop the recording, remembering that this full video will be available in the YouTube, and the link will be in the Brazilian Logic Society website.
Okay, great.